Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week, I'm happy to bring you my interview with Calvin Seward, a research scientist with Berlin, Germany-based Zalando. Now, our American listeners might not know the name Zalando, but they're one of the largest e-commerce companies in Europe with a focus on fashion and shoes. Calvin is a research scientist there, while also pursuing his doctorate studies at Johannes Kepler University in Linz, Austria. Our discussion continues the Industrial AI series here on the podcast and focuses on how Calvin's team tackled an interesting warehouse optimization problem using deep learning. Before we dive into the show, take note. This is the last podcast before we give away not one, but 2 tickets to the AI conference in San Francisco, brought to you by O'Reilly and Intel Nirvana. If you've listened to the podcast for a while, you already know that this is one of my favorite events, and you've already heard some of the great speakers that it attracts. If you'd like to attend, now is the time to enter our giveaway. Folks really seem to like our new streamlined contest app that makes it super quick to make up to 10 contest entries. To get your entries in, just hop on over to twimlai.com/AISF and stay tuned for our announcement of the winners on next week's show. And now, a quick shout out to our sponsors, Bonsai and Wise.io at GE Digital. You've heard me mention Bonsai before. Bonsai offers an AI platform that lets enterprises build and deploy intelligent systems for industrial applications and more. Bonsai's platform lets enterprises develop robust machine learning models that improve system control and enhance real-time decision support. Their platform also automates the management of deployed machine learning applications, allowing businesses to use them to increase automation and improve operational efficiency of industrial systems, including robotics, manufacturing, supply chain, logistics, energy, and utilities. You can find more information about Bonsai and their early access program at bons.ai/twimlai. And undoubtedly you know GE, but did you know that GE was a software company too? GE Digital is a leading software company focused on solutions for the industrial Internet of Things and is reimagining industry's infrastructure for connecting software, apps, and analytics to industrial businesses. GE Digital creates software powered by their Predix platform to design, build, operate, and manage the entire lifecycle of physical assets, enabling industrial businesses to operate faster, smarter, and more efficiently. The Wise.io team, now part of GE Digital, is building industrial machine learning applications for GE and its customers. For more information about GE Digital, visit ge.com/digital. And now, on to the show. All right, everyone, I am on the line with Calvin Seward. Calvin is a Berlin, Germany-based research scientist at Zalando, and he's also pursuing his doctorate at Johannes Kepler University in Linz, Austria. Calvin, welcome to the show.
Welcome.
Folks who are listening to the show know that I was recently in Berlin, and I, in fact, connected with you while I was in Berlin, but unfortunately, we weren't able to connect locally, but we're connected now. So I'm really looking forward to diving into our topic today, which is some work that you did not too long ago on warehouse optimization. But before we dive into that, why don't we spend a little bit of time having you introduce yourself to the audience?
Yeah, thanks. So as I said, I'm Calvin Seward. Originally, I studied mathematics at the Humboldt University here in Berlin. And since then, I've been working at Zalando. And so Zalando is the tech company that nobody's heard of. It's a very large online retailer based in Germany. And so it's more centered on fashion retail in the European market. So it's well known in Europe, but very not so well known in the rest of the world. And in addition to working at Zalando, I also am pursuing my doctorate. So the doctorate program, it's a cooperation between the Johannes Kepler University in Linz in Austria and Zalando. And so it's really nice. It's really fun because I I get to do research, but I also get to use Zalando's resources, Zalando's data. And so it's a really cool thing.
Oh, that sounds like a great opportunity.
It really is.
How did you initially get interested in artificial intelligence?
Somehow my career, it's always just been like, whatever the next thing is, just do it. So I studied statistics. And so then when I started at Zalando, I was one of the first people doing data science. And I don't even think my title was data scientist. It was like data analyst or something like this. And so
Mm.
at the beginning, we just did ad hoc reporting for management, trying to answer questions like, oh, should the article breadth be broader, or so should we have more articles, more different articles, or should it be deeper? So each article have more time so that it doesn't get sold out so quickly. Answering questions like that. And then
Hmm.
slowly but surely, the low-hanging fruit got dealt with, and it became apparent that in order to keep up with the competition, we had to step up our game. And so that's how we got interested in artificial intelligence, because it was definitely the next big thing, and is something that can drive a lot of customer value.
Maybe you can tell us a little bit about the warehouse optimization problem that you've worked on.
Yeah, what we did was we first had one project called the Okapi project, where you can imagine the inside of warehouse. It looks like an offline retailer, actually. It looks like Target or Safeway or Tesco or Kaufland, or I don't know which country my listeners are going to be sitting in, but just one of these
Hmm.
large, or Walmart, one of these large stores with a bunch of aisles with items and cross aisles, and people walk through these store with shopping carts, and they put items in the shopping cart, and then they go to checkout and leave. And so it's the same way in the offline, or in the online warehouse. So what happens is our workers, they start off at this thing that we call the train station, and they pick up this cart that's empty, and then they walk through the aisles and the cross aisles, and they put items into their cart. And then when they've sort of completed their shopping list, they bring the cart back to the train station, and it's sent on to be processed, and for the items to be sent to the customers. So then everybody knows when they're shopping that there's an efficient way and there's an inefficient way to walk through the store. And so you first buy your butter and your milk, because those are close to one another, and then you go off and buy the bread. You don't do the butter, then the bread, and then the milk. And so it's the same way in the online warehouse, that we want to know how to order the shopping list so that the worker
Hmm.
can walk through the warehouse in the optimal way. So this is sort of a traveling salesman problem, where you have a bunch of different locations that the worker has to visit, and then you want to be able to tell the worker how to visit the locations in the most efficient way. And
Hmm.
so there was some research that was done about how to walk through the warehouse if the warehouse has a specific layout, and it's this so-called rope ladder layout. And so it's the same layout that you have in most large offline retail stores.
And the rope ladder layout is, well, tell us specifically what that means.
Is you have aisles and cross aisles,
Hmm.
and each cross aisle, or each aisle, is the same length, and they have and they're aligned with one another. So it's not like you have this weird jog that you have to make.
Okay.
So
So it's kind of a simplification. And I guess now that I'm visualizing it, rope ladder is, just simply trying to create that visual of two long rows with a bunch of cross aisles, that kind of thing.
exactly, it looks like a rope ladder.
Got it.
Yeah, and so there was some work that was already done on optimizing for this setup, but what was missing was the people who work in the warehouse. They have these big carts that they push around, and they're actually
Hmm.
quite large, because they can carry a lot of items,
Okay.
but they're sort of difficult to handle. And so it's the same way if you're shopping offline. If your cart is fairly full, then you generally leave it in the cross aisle, and you walk into the aisle without the cart and collect your items, and then return to the cart. And
Mm.
so we wanted to be able to tell the workers, okay, how best to handle the cart. So we extended this algorithm, and we come up with this algorithm that we call the Okapi algorithm. And so this is called optimal cart pick algorithm. that's able to tell the warehouse workers how best to walk through the warehouse and where to leave the cart, so that the warehouse worker knows he can always just leave his cart where the algorithm suggests it, and then walk to the different locations and get the items, and he knows that the algorithm will always bring him back to the cart before he gets too much stuff that he can carry. Yeah,
Okay.
too many things to carry. And so this has absolutely nothing to do with machine learning. Let me just say that. So if the
Hmm.
people think, oh, where's the machine learning? It's still not here yet. This is a fairly straightforward discrete optimization problem where you have this list of items and you have to decide how to order the items. You have these lists of cart locations that you can put the cart, and you've got to insert the cart locations in there somehow. And then you've got to optimize this guy. It's a dynamic programming algorithm, so the optimization works. It's linear in the number of aisles, so it's got a reasonable enough complexity.
Okay. Before we move on, you mentioned traveling salesman problem, and folks that have done any work in computer science would probably be familiar with that. But in case there are folks that aren't familiar with the implications of something being essentially a TSP, what does that mean in terms of how we know how to solve that problem?
Oh, there's lots of literature on solving traveling salesman problems, but at the end of the day, it's an NP hard problem. So NP hard means that it's something that, in the most general case, is exponentially complex. And so there's lots of heuristics about how to solve it. But you can imagine that this traveling salesman problem. So the idea is the place that the name comes from is you have a bunch of different locations, and you have some salesman, and he starts at his house, and he wants to then go visit all the locations, and he wants to do it in a way to where the distance that he travels is minimal. And so there's lots of heuristics on it, and obviously if the locations are organized in a nice way, then how best to do it is fairly clear. For example, if all the dimensions lie on, or all the locations lie on a one-dimensional line, then it's fairly clear how best to travel. But already in two dimensions, it becomes difficult. So this rope ladder warehouse layout is one of these special cases. You can think of it like the single dimensions case where you just have a line. It's a special case to where you can efficiently solve the traveling salesman problem.
Okay. And then you mentioned your cart handling strategy component of this, where you're trying to figure out where the worker can park their cart. Do you also need to consider anything along the lines of bin packing or cart capacity or anything like that?
Yeah, I mean, it's something you can consider, but at the end of the day, it's not a huge deal
Hmm.
because basically you just try and make the pick list as large as possible. And then if the cart gets too full, then there's a button for the warehouse worker where he just says my cart is full, and then he goes back to the train station and gets a new cart, and the system deals with that.
Okay.
So that's not really a big problem.
Okay. And so you mentioned that the formulation of this problem, this Okapi algorithm, is, we're at discrete optimization. It's not yet machine learning. How is the discrete optimization problem solved in practice?
So for us, it's a dynamic programming algorithm. That's what it's called. And so I mean, there's a couple of articles online. You can Google it where I explain this. So let me try and remember how best to explain it. But the idea of dynamic programming is that you know that there's a lot of different combinations, but each combination will there's these transitions between combinations, and they can only take on a certain finite number of states. And so you just look for the best combination for each transition. And so the way this looks in practice is imagine we have our rope ladder layout with only two cross aisles. Okay.
Okay.
And then imagine we sort of split it in half. All right.
Hmm.
So then there's these two cross aisles. And we're not, don't think about the cart. We're not thinking about the cart. We're just thinking about the optimal way to walk.
Okay.
Then there's a couple of different things that can happen. Either the worker, he doesn't walk. So these two cross aisles, these two little cross aisle sections that are in the middle, okay?
Mm-hmm.
So either the worker doesn't walk on those. So that means that his entire pick route was either the left or the right.
Mm-hmm.
Or it can happen that he only walks. So he's got to return to where he started. Yeah. So that means that he walks once on both of them. So he
Right.
walks on the top cross aisle, he walks once, and on the bottom cross aisle, he walks once. All right?
Mm-hmm.
Or it's possible that he walks twice at the top, or it's possible that he walks twice at the bottom, or it's possible that he walks twice at both the top and the bottom. So these are all the different states that are possible. And
Mm-hmm.
so what you can do then is no matter what your optimal solution is on the left, and no matter what your optimal solution is on the right, they're going to have to communicate with each other via these 7 different states. So if you can sort
Okay.
of recursively find the optimal solution for the left, what you can do is then you can recursively find 7 different optimal solutions for these 7 different transitions. I don't remember if it was exactly 7, but for these 7 different transitions, you can know, okay, what's the optimal solution going to be? And then you
Mm-hmm.
just calculate, okay, what's the optimal route for the next cross aisle or the next aisle section, and for these 7 different transitions, and then you do that recursively until you get to the end. And so then instead of having to think about every single different combination, you're always just trying to figure out, okay, what's the best one for these 7 different states.
Okay, if I could try to paraphrase that, we're looking at this warehouse with this rope ladder configuration, and you can basically, chunk it down into, sections of the rope ladder with 2 cross aisles, and then solve the optimization problem locally. And then that's all kind of strung together recursively to give you an overall optimal strategy.
Exactly.
Okay.
It's hard to explain. The first time I read the paper, I was also like, what's going on here?
I also saw you mention in some of your writing simulated annealing. Is that this process that we just described, or is that something different?
Okay, no, so that's definitely the next step. So
Okay.
now what we got this Okapi algorithm. So Okapi is short for optimal cart pick.
Okay.
And it works well, but since we have larger warehouses that are more than just 2 cross aisles, and since we have this cart business going on, it takes like a second or so to calculate what the optimal route will end up being. All right?
Okay.
So if you're just trying to figure out the route for the warehouse worker, you already have your pick list together, then it's fine. But the next step is, of course, to optimize the pick list, because
Mm-hmm.
every day the warehouse workers pick hundreds of thousands of pick lists, and if you can optimize these to where each pick list has items that are fairly close to one another, and optimize it to where the pick lists are fairly large and batches don't have to be picked from very many zones of the warehouse, then this is a real good thing. But in order to do this, you have to sort of know how long a hypothetical pick list will end up being. And this 1 second thing is really a big constraint, because then you can't try out, thousands and thousands of different combinations without racking up a huge Amazon Web Services bill that's prohibitive. So what we did is
So just to make sure I'm understanding there, with this Okapi algorithm, that'll give you basically the routing for an individual, pick list and picker. And then in order to figure out the best way to organize the pick lists and like the orders, you have to just brute force that. So you go through and run this Okapi algorithm a bunch of times with a bunch of pick lists. Is that the idea?
Yeah, well, I mean, even if you're using simulated annealing, you still have to. I mean, so yeah, there's methods better than brute force, like simulated annealing, but even there, you have to try out a bunch of different combinations. So
Okay.
you're never going to get around having to try out a bunch of different combinations of pick lists to see which ones end up being super long and which ones end up being quite reasonable.
And so your problem comes in when it takes 1 second to try out one of these combinations, to do that at scale takes a really long time.
Exactly.
I think you had an example of, I don't know if this mapped to kind of a real life Zalando configuration, but like 2,000 years
Yeah, exactly. It's like Jesus would order his shoes and he still wouldn't have them now.
So you've got the two problems, and your focus was on trying to reduce the time it takes to calculate. Is it to calculate an optimal route or to calculate the length of a route given a pick list?
Yeah, to calculate the length of the optimal route given the pick list.
Got it. Okay.
We're not actually calculating for this stuff where we're trying to figure out which order goes with which pick list, or which order should be in which pick list. We don't actually have to know what the route should be. We just need to know how long the optimal route would end up being.
Okay. And so we want to decrease that time because whether we're using brute force or simulated annealing or some other kind of heuristic, it's still going to be dependent on the amount of time it takes us to figure out the length of the optimal route for a given pick list.
Exactly. So there's two different levers we can pull to speed things up. One is, better simulated annealing heuristics, and the other one is just make this bottleneck, which is calculating the length of a pick list, faster.
Mm-hmm. All right, and that's where machine learning comes in.
Exactly. Now we're finally going to get to machine learning. I hope the audience is still with us right now.
I'm sure they are, because this is their time.
Okay. If you've been tuning out, now's your time to tune back in. So what we do then is we use the Okapi algorithm to generate data that we learn on. So we just generate millions and millions of random pick lists, and we put these through the Okapi algorithm. So we had a bunch of different CPU cores just running at the same time, taking a random pick list, calculating how long that would take, and then spitting out the answer. And so these computers, they generated our training data. And then with this training data, where we've got pick lists, so we know where the articles are that need to be picked and how many there are, and how long it would take for the optimal route to get picked. So given these two guys, we can then feed this information into a neural network and train that neural network and get some sort of a good result. And so there's lots of stuff you can simulate, yeah, and some of it will be good for neural networks, and some of it probably won't. For example, if you think of some sort of a fancy hashing algorithm that tries to avoid hash collisions, you can obviously simulate this, but you wouldn't be able to get a neural network to give you the same output, because the whole idea of hashing algorithms is that it's as non-continuous as possible. Mm-hmm. But for this copy thing, it works very nicely, because you can imagine if you just have one pick and you move it around in the warehouse, if you just move it a little bit, it won't change the pick route very much. So if you move it a little bit in the cross aisle or in the aisle, it won't change the pick route very much, because the worst thing that can happen is if you move it, a foot, the worst thing that can happen is the warehouse worker has to walk an extra foot to get there. It's not so linear in the cross aisle. So if you have a pick that's in the middle of the aisle and you move it the next aisle over, could be that it creates a big jump, because then the warehouse worker, he may have been going to that aisle already, and then this new aisle, he wasn't planning on going there, and so then the distance is quite a lot larger. But still, it's it's not these huge jumps. So
right.
So that's one reason why it's a nice thing to model with neural networks. And then the dependencies between the articles are also nice, because obviously it's not just some linear sum. If this article is here and this article is here, the distance that the guy has to walk is the sum of the two distances, but it's this complex dependency between all the different articles. But this is sort of more locally dependent. So it's less of one of these situations where the butterfly's wings in Japan cause an earthquake in LA, situations. But it's
Right.
more that as you shift articles around, it really only has it generally, I mean, sometimes there's exceptions, but generally it really just has an effect on how the warehouse worker walks in that area, and it doesn't have too much of an effect on far-flung corners of the warehouse. And so
Hmm.
because of this, because we don't have too many jumps and the function is somewhat continuous, it makes it to where it's good for neural networks. And
Hmm.
because local structures are more important than global structures, we can use convolutional neural networks because the convolutional filters, they only focus on local features, and then they combine these local features together as they move up through the hidden layers.
Mm. So then let me take a second to kind of recap. Basically, we want to get the time to figure out the optimal path length for this, for picking an order down. Neural networks is probably a great way to do that. And essentially, what we're trying to do is we're trying to train a neural network to approximate this Okapi algorithm. And we do that by generating a bunch of random pick lists and throwing them through the Okapi algorithm to generate the path length. So basically generating our training data through by throwing random data through this Okapi algorithm and then using that to train our neural network.
Exactly. Exactly.
And so I guess one question that I've got is you found that at 1 second per route to run things through this, or it takes a second to run a route through this Okapi algorithm. And in order to, fully explore the state space for like a real warehouse, it would take 2000 something years. If you did all of those, how much coverage do you need in order to, accurately train a neural network to do this? What percent of that state space, or how many training samples do you need?
Well, we didn't really say, oh, we have to have exactly this accuracy, but we just said, oh, we've got this machine here. Let's create enough pick lists where the machine runs for a week or so, and then because we've got other things to do this week, and then next week we'll come back and look at the results. So that's the way it works a lot of times. And then
Mm-hmm.
we looked at the
Got it.
results and we're like, it's good enough. And then
Okay.
that's how it happened. So it wasn't like we explored, oh, how many pick lists do we have to create to get this accuracy, but it was just sort of these practical considerations that were more
Got it.
at the forefront.
And then, I typically associate convolutional neural nets with image processing types of tasks, but yet it worked in this case based on this locality aspect of the problem. Did you have to jump through any intermediate steps to kind of format the process or format the input data so that it looked like an image, or are you just kind of feeding it, data that, was natural to the problem and, without any kind of intermediate steps?
I think that at the end of the day, we used Cafe for this. So this was back in the dark days before TensorFlow.
Mm-hmm.
And so there you had different input layers, and I think we figured out that the TTIF, it's an image format. I think that we figured out that that was the most convenient layer to use. So yeah, the pick lists, we transformed them into a TTIF image, and we
Okay.
fed these images in there.
Okay. Interesting.
But I mean, this is really just a stupid technical detail.
Right.
It was just because of the different input layers in Cafe. And so if we'd done it with TensorFlow now, it would have been a whole different story.
Okay. And so you used a convolutional network to model this. How did you arrive at the ultimate architecture of that network and the number of layers and the configuration of those layers and all that stuff?
Oh, we tried out a couple of different things, and then one of them worked, and we were happy. But
Okay.
I mean, there's a little bit of dark arts to this sort of thing.
Mm-hmm.
And we knew sort of like what the interactions are between different articles, and so we said, okay, because of these interactions, maybe the filter size should be about this large, and we knew how complex the interactions could be. So the depth of the network should be around here, and then tried out a couple of different combinations. And at the end of the day, I mean, these TTIF images were not particularly large, because
Mm-hmm.
each aisle is then one pixel, and each cross aisle, and then the depth of the cross aisle, that's then or the depth of an aisle is then sort of an approximation, because obviously these articles are located at some discrete spot, or at some continuous spot, but you have to make it into a discrete pixel. So it's a little bit of an approximation,
Mm-hmm.
but who cares? And so the images were not particularly large, so we were feeding through, and so you could train it very quickly, and within the course of a day, and just try out a bunch of different things and just see what works best. Be done with it.
Okay. All right. Awesome. And so you did that, and what were you able to accomplish in terms of getting your time down that you were trying to accomplish?
Oh yeah, no, that was really good. So I don't remember the exact numbers, but it's definitely under a millisecond. So I did a benchmark, and that's in one of the blog articles, where we just then ran it, and we had different configurations, because obviously with this sort of thing, it's a whole lot more efficient if you don't just calculate one pick list, but calculate a batch of pick lists together.
Mm-hmm.
And so if you're able to take your pick lists and put them in a big batch and calculate that whole batch, and if you had a large enough batch, maybe 30 or 40 pick lists, then you were well under a millisecond. And so this was a huge improvement.
Okay. Awesome.
Yeah, and also just, I mean, you didn't even have to use fancy hardware. A millisecond on the CPU. Yeah. So if we had used the GPU, sure, it would have been even faster. But
And the millisecond corresponds to inference against the trained network,
exactly,
as opposed to, and that's why it's so fast.
Yeah. Learning is obviously a little bit slower, because there you have the forward pass, the backwards pass, the weight updating, and all this other business going on.
Mm-hmm.
And so that you really want to do on the GPU. But when you're just inferring afterwards, it's a small network, so you can just infer small pictures, small network, so you can just infer on the CPU, and you're already very fast. And obviously for when you're deploying it to a live system, people always like it when you can deploy it to a large number of different hardware setups, and you don't have to have one specific GPU. So that's always a big advantage.
Awesome. So you solved this problem. Where did you go next?
That was one of the last warehouse problems that we actually dealt with, because at the end of the day, you can think of it this way, if you solve these warehouse problems, it's really great, because it makes it to where fulfillment costs are lower, the item gets there faster, so everybody wins. The customers, they're happier because they don't have to pay as much for fulfillment costs. We win because we don't have to have such large warehouses, because everything works more efficiently. But at the end of the day, the maximum, win you can make is whatever your fulfillment costs are. If you can manage to be so efficient that fulfillment is for free, then that's the maximum you can get. Whereas if you develop new products that really excite customers and make it to where you can engage with customers who weren't engaging with you beforehand, the potential winnings are, just through the roof. There's no limit to that. And so we said, okay, we want to try and get away from just incrementally eking out a little bit of efficiency here and there, and we want to get into things that really create new ways of interacting with fashion and interacting with e-commerce. And so I think you see this a lot. I go to a lot of industry conferences, and I really see this a lot, that there's this progression in companies, and the first thing that they do is they have all this data sitting around, and the first thing they do is they realize, oh, we can use this data to drive efficiency. That was one of the first projects that I helped contribute to, was this forecast where we tried to predict which articles would be returned, so that we could have enough workers at the warehouse on the day that these articles would be coming back, because we didn't, the customers, they just put them in the mail when they want to return them. And so we don't really know how many articles are going to come to us on a given day. Yeah, but
Okay.
we were able to use data and fairly accurately predict which articles were going to be returned when and make it to where the right number of workers were there. So it was a driver of efficiency, is very nice. So a lot of companies, that's the first thing that they do is they take some sort of existing process
Hmm.
and they make it a little bit more efficient with data science and with machine learning. And then you can go to the next thing, which is this project that I've talked about now, which is you create new processes that drive efficiency through data science.
Mm.
So any sort of consideration of how to split the pick lists or split the orders between pick lists to optimize the actual walking distance. This was completely impossible without Okapi. So no one even thought about trying to do it. But
Right.
by having Okapi, you were able to come up with new processes, and by having data science, you were able to come up with new processes that drive efficiency. But for the customer, nothing has changed. There's absolutely no new products.
Right.
For him, it could have been, just a bunch of business people sitting around, coming up with business rules. He doesn't notice the difference.
Hmm.
But what's really great is when you can then come up with new products like a really great recommender, really great search. All these self-driving cars is obviously also an example. We don't have that. We're not working on that. But these are products that are genuinely new and wouldn't have been possible and are new for the customer too. And this is where the big future is at.
Mm. It's interesting that your examples are recommenders and searches. I think of those as kind of these existing things that we do, much like the warehouse. We do them, using either brute force or, brute force-ish things that feel like brute force in their sophistication and not necessarily like, wholly new kind of user experiences. Do you have some examples of the way that you're thinking about recommendations in search that illustrate, where the new opportunities come in for you?
Yeah. So it's a great question because yeah, obviously, for example, for document search, you can always have some strange business rules that come up with documents. But I guess you're old enough to remember, what searching the internet was like before Google came around.
Mm-hmm.
It was a completely different animal. Yes, there was
Right.
search, but it was so frustrating.
Right.
And it's the same way with like old speech recognition systems. Yes, there were systems, but they were so frustrating that it's as if, if something's unusable, then it's pointless?
Uh-huh.
So I'm saying, sure, you can always come up with something that does something, but if it's so frustrating, then it's pointless. And it's the same way
Mm-hmm.
with self-driving cars. I mean, even back in the day, they had these cars that somehow were able to tell where the line was and stay between it, but they were in no way, shape, or form safe. And so, what's the point
Right. Right.
if it's this Russian roulette? But by using data science, you can cross this threshold between something that's unusable and something that's usable. And
Mm.
that's what I mean by enabling a product that's usable. That's
Got
what
it.
I guess I mean.
Okay. Before we
And
leave
okay,
the
and so
Go ahead.
to extend this, there are different ways of searching. The classic search is just you have it's this sort of document based search. You have your text field, you type something in, blue dress or whatever, and then you get a list of blue dresses. And I think that there's definitely ways that we can improve this. So we came up, for example, with a Tinder for fashion articles ones where you swipe left, swipe right, and you get
Mm-hmm.
shown different stuff. And so it
Okay.
wasn't all that usable, but it was a fun thing, and it was like just a way of showing that search can be different than box at the top and then display results at the bottom.
Right. I've also seen companies in this space experimenting with image-based search, similarity, things like that. Is that the general direction that you guys are headed with this kind of stuff?
Oh yes, definitely, definitely. I mean, fashion. It's so. I mean, if you're like searching Amazon, they start off with books, and then when you search for a book, it's fairly simple because
Right.
you don't judge a book by its cover, you search for the author and the title. But in fashion, you do judge a dress by its picture. And it's
Right.
very difficult to, even for experts, to describe a dress, use words to describe exactly what it's going to look like. And
Mm-hmm.
so, and then if you have a layperson and they're trying to wade through our huge assortment and trying to find something fairly specific in this assortment with over 100,000 articles, then it's going to be very difficult for them to find the right article unless we have more clever search things than just using metadata, just
Right.
using some description that some people have hand annotated.
Mm-hmm.
Which obviously it works for books, it works for computers. You just sort of say what sort of RAM you want, what sort of processor you want, and bam, you've got your results. But you can't do that with dresses and
Mm-hmm.
fashion articles.
I guess when I think of how that process is done today, not necessarily for fashion, but with other e-commerce search experiences, it seems like that search and research experience is largely driven by, as you said, metadata. In the fashion space, to the extent that it's currently, still driven by metadata, where does that come from? Is that, I guess you already said, it's basically it's all handcrafted, right?
Yeah, it's handcrafted, and it's been a very open question as to how to extract data from unstructured, or how to extract useful insights from unstructured data. And pictures are very much an unstructured data. But like one thing that you can do that's fairly easy, even with today's understanding, is it's fairly easy to come up with neural networks that are able to say if fashion articles are similar or dissimilar based on the picture.
Mm-hmm.
And then you can use this similarity measure to help improve your recommendation system. So then at the bottom it's always like, oh, customers who like this also clicked on this, and then you can improve the recommendation experience that way.
Mm-hmm.
That's definitely an easy low hanging fruit, even with today's image recognition stuff.
Okay. Well, let me ask you this. When you're working on a problem like the warehouse optimization problem, where there are existing processes, or if not existing processes, existing costs associated with that, and you're comparing that to something that is more or less wholly new, like a new user experience for discovery or for searching for items, it strikes me that you have to take a very different approach in building out the business case for these two types of things. And that, depending on the culture of an organization, the management team, et cetera, it may be more difficult to do one than the other. Do you have any insights on navigating that process based on your experience working across these different types of problems and as you described it, kind of the maturity of, starting from, one type of problem and moving to the next and then moving to the next?
Yeah, that's a really great question. And I would say that the most important thing is that you have management that's forward thinking enough to know that these sort of things is not an easy win, and it's not a win that happens immediately, but it's something where you have to invest for a while before you get something good, and you really don't know exactly how long that's going to take. So management is really important. And then these managers, they then have to say, okay, we're going to not try and devote all of our resources just to the next release cycle, but we're also going to devote some resources to things that are not going to pay off immediately. And so I work in Zalando research, and that's what we do. That's what we try and focus on, is things
Mm-hmm.
that are more of long-term benefit and less short-term. And so it's really great that the Zalando management team has decided that this is a really important thing, and this is really something that I find hard to find in a lot of companies, and so I'm really happy about this. And then from our perspective, it's helpful to not put all your eggs in one basket. So don't just focus on one deliverable, but focus on a portfolio of deliverables. So we try and focus on four main things. We focus on prestige is one. So things like what I'm doing right now with talks and podcasts and generating excitement for Zalando and the great research we're doing. We focus on products, new products. We focus on papers, so academic publications to really sell the great research we're doing within the academic community. And we focus on patents, patenting. Whenever we come up with new ideas, we patent them because the patent portfolio is also very valuable.
Interesting. So you mentioned prestige, patents, publications, and some other things. It sounds like from that you guys are very active out in the machine learning community as well as the e-commerce communities. How can folks in the listening audience who want to learn more about the kinds of things you're doing, how can folks find you and find all that good stuff?
That's a great question. We have a tech blog, so the Zalando tech blog. And it's not just us that writes this blog, but there's lots of different techies at Zalando who write to this. And there's also a Zalando research page where different projects are detailed that we're working on. Those are two great ways to get started. If you like what you see, you can always send us a job application. We're always looking for new, excited data scientists and researchers. So those are two great ways to get into what we're doing.
Awesome. And I'll include links to those in the show notes.
Yes.
Calvin, I really enjoyed this conversation. Thank you so much.
Yes. Thanks for taking the time.
All right, everyone. That's our show for today. Thanks so much for listening and for your continued feedback and support. For the notes for this episode, to ask any questions or to let us know how you like the show, please leave a comment on the show notes page at twimlai.com/talk/38. Thanks again to our sponsors Bonsai and Wise.io at GE Digital. For more information about Bonsai, visit bons.ai/twimlai, and for more on GE Digital, visit ge.com/digital. Once you're done with this show, take 30 seconds to head over to twimlai.com/AISF to enter our giveaway for a free ticket to the AI conference in San Francisco. You could be one of 2 lucky winners. For more information on industrial AI, my report on the topic, or the Industrial AI podcast series, visit twimlai.com/industrialai. Thanks again for listening, and catch you next time.